right. For those of you who don't know me, my name is Joshua Watt, and I'm going to talk to you today about some changes that we've made to the Hash Equivalence server to help us run it at scale on modern web-based infrastructure that you might be used to. So, a little bit about myself. I've been working at Garmin since 2009, and we've been using Open Embedded in the Octa project since about 2016, mostly to make marine products, so electronics that go on boats. I'm a member of the Open Embedded Technical Steering Committee, and there's all the different ways that you can contact me if you need to do that. So what is a hash equivalence? It's a build acceleration technique, as was described in the previous presentation, where basically BitBake can ask if a given hash that it's calculated for a task is equivalent to some other task, and therefore it can skip the actual build and restore something from S state instead of building it. As stated, this is useful when there's changes to a recipe that cause the hash to change, but not the S state output. So this would be like white space changes or like code changes or changes in code that isn't actually compiled into the final output or whatever it happens to be. Just to kind of describe a little bit visually how this works, basically what happens is when BitBake is preparing the run queue to try to figure out all of the tasks it needs to run, it will calculate hashes for them. And then for each hash, it will ask the hash equivalence server, hey, I've got a task hash ABC123. Is there anything that's equivalent to that? And the hash server will respond and say, yeah, that's equivalent to this DEF456 hash or whatever. And BitBake will then use those uni hashes, as we call them, in place of the task hashes when looking for S state objects. So it'll say, oh, great, that lives in S state, that uni hash lives in S state, so it'll just pull it from there instead of actually building the thing. And then while it's actually building tasks, running tasks, when it's done building something that goes into S state, it will calculate a hash of the contents of what's in the S state object and then report that to the hash equivalence server. So it'll say, I built this task hash, 987 FED, and its content hash is this 654 BCA. And the hash equivalence server will record that in its database and then might report back something like, oh, that's actually equivalent to unihash 321 AAB. And when BitBake sees that, it will go then recalculate the task hashes for all the downstream dependencies of the task it just ran using that new unihash instead of the original task hash that it had. And then it might be able to restore some of those downstream dependencies from S state instead of actually building them. So those are that's kind of a very high overview of how it works. So the current hash equivalence implementation is the clients connect to the server using either a Unix domain socket or a raw TCP socket. Messages are sent back and forth between the two based on a JSON protocol, a line-based JSON protocol. So every line in the stream is a JSON object that gets deserialized. The client is implemented using Python's async IO support, and then there's this thin wrapper on top of that that could be used to turn that into a blocking API if you don't want to be implementing async IO in your application. The server is implemented completely using Python async IO, and it stores the database in a file using the SQLite module. So the reason a lot of these choices were made is that this doesn't require any third-party modules for Python. So this is all using the batteries included Python modules that come with Python. You don't have to pip install anything. All you need is Python, and this will work on either the client side or the server side. And since we like to keep our dependencies very minimal in BitBake, this is very nice for that. There are a few downsides to the way that this was implemented, though. One of them is that it's difficult to scale the server for a higher load for a couple of reasons. So first of all, the async IO, well, it's great because it can service multiple clients at once. It is just single threaded. So once you have saturated a single CPU core with the server, it basically can't do any more. Now, a lot of what the server is doing is things that are like blocking calls. So that is a fairly high load, which is a stock server, but it is something to keep aware of. You're probably going to have trouble scaling to hundreds or thousands of connections if you need to do that. In addition to that, raw TCP sockets in and of themselves are somewhat difficult to load balance using on modern infrastructure. So if you're familiar with like modern web-based infrastructure, you put a reverse proxy in front of your HTTP endpoint and you can load balance out to any number of instances of a server. That's a little harder. It's not impossible with raw TCP sockets, but it's just not as easy as something like HTTP where you just run Nginx and you're done, right? Or not Nginx, that's not the load balancer, but whatever, you run the load balancer and you're done. And then in addition, the SQLite calls that it makes are actually blocking. So any call to SQLite blocks the entire server and prevents it from servicing anything while that SQLite call is going on. And basically the reason for that is that the SQLite module in stock Python doesn't have async IO support, so they have to be blocking for that. In addition to that, TLS is kind of annoying to deal with if you have requirements that you need to use TLS or, for the client or the server. It's not impossible, but trying to do things like TLS termination with raw TCP sockets isn't the easiest thing. Again, you can do it, but it's not as simple as just putting a reverse proxy in front and doing TLS termination there. And again, at the client level, if you need any sort of like abnormal certificate setups or anything like that, that can just be a pain to have to bake all of that into the server application itself instead of just using something on the front end. And the same with the client. Sharing the database between multiple instances is also kind of difficult. It's pretty easy if they're all on the same machine because it is just a file. So as long as they can all access that same database file, everything is fine and it will just work. But if you start talking about containers or multiple VMs or things, it gets a lot harder to share that file in a reasonable way. In addition, like related to that, like a dedicated SQL server is definitely preferable for scaling because you can put that on some big iron database machine and it will scale a lot better than the SQLite module in Python. And then in addition to that, the server doesn't really have very fine-grained controls over user permissions. And some places have requirements for that thing, especially as we add more support to the server, it becomes more apparent that you might want that kind of thing. So right now the server only has two modes. There's normal mode where every client that connects can do whatever it wants. And there's a read-only mode where clients can connect, that you run the server in and clients can connect. They can read hashes, but they can't report anything. That the API still quote unquote works, but it doesn't actually write anything to the database. It just reports back what it should be. And then they can't do any of the database management APIs or anything like that. So we've done a bunch of things to try to help make this better. So one of the first things that we did is we transitioned to be able to use WebSockets as the transport mechanism. This is using the exact same JSON messages that the Unix domain socket and the TCP sockets use. It's just they're in a WebSockets packet instead of lines on a raw protocol. And this was implemented using the third-party WebSockets module, but only if you actually enable it. So unless you are talking to a WebSockets server using the WebSockets protocol, as is shown with the addresses down here, it won't try to import the WebSockets Python module. So you don't have to have it installed. So we can still keep that minimal dependency footprint unless you actually need WebSockets support. And because WebSockets are all based on HTTP and very standardized web technology at this point, like they're much easier to route through reverse proxies, do the TLS termination, the load balancing, and all of that other stuff on the server side. Basically, we don't have to deal with any of that in the server itself. We just say, hey, we're WebSockets, and all that stuff you put on the front end and basically call it a day. And then again, the same on the client side, like the TLS is basically free. We didn't have to do anything. It just sort of works. You do WSS, you get a TLS WebSocket. And then this was implemented in such a way that it's designed to be very easy to backport the client support to older versions of BitBake. It's just 2 patches, and they should apply cleanly several versions back of BitBake. They're currently just on master, yeah, so it's designed to be backported very easily on the client side so that older BitBakes can talk to newer WebSockets enabled servers. Another thing we did is that we transitioned to using an actual ORM for the server database. This was done, we chose SQL Alchemy for this just because it basically supports everything and it's very easy and it still supports the async IO support that we need. And again, that's all optional. If you don't run a server that isn't using SQL Alchemy, it's not going to import the module, so you don't need it installed. The SQLite backend didn't go away. It's just a different backend that you can choose. And we actually would recommend SQLite for smaller installations just because it has less overhead. It's a little faster and more responsive on those smaller installations. This allows us to get fully asynchronous database queries on servers that use SQL Alchemy, so there is no blocking at all of the server when it's making an SQL query. It does have higher throughput, meaning it can handle more simultaneous clients, but it also has higher latency. So if you're not running a server that needs to handle a lot of clients at once, you might be better off just running keeping with the SQLite backend. But if you want that big iron database on your backend, this is definitely the way to go. Another thing that we added was user authentication and permissions. So this allows clients to optionally authenticate themselves with the server, and then users can be assigned fine-grained permissions about what they are able to do on the server. So there are 5 permissions. There's read, which lets you read hashes from the server. Report, which lets you report equivalent hashes while you're building. There's a DB admin permission, and it lets you do database administration, cleaning up entries in the database, and other stuff like that. There's user admin that lets you create, delete, change user passwords, all of those user admin-y things. And then the last permission is all, which is which means all permissions and any we might add in the future. It's basically the super user permission. And then what you can do is you can actually set what the anonymous permissions for the server are for users that choose not to authenticate, which might be older clients, won't make the authentication call, so they'll be the anonymous user. Or if you don't want your users to have to put in their passwords and stuff, you can just set what the anonymous permissions are, and then it won't authenticate. If they don't authenticate, that's what they get. This defaults to read, report, and DB admin. That's for backwards compatibility. That's because basically that will get you all the permissions that exist on the server today. So if you upgrade the server, you won't lose functionality by upgrading. This is not a very secure default. I would recommend making it either at read or at none. There's another permission called none that I didn't report here, which means nothing, which would just allow you anonymous users to read the database. You could do read report too if you wanted, but I'd probably remove DB admin when you upgrade. The way the authentication works is that the server will generate a random password for you, a random token, and then users basically use that token when they want to log into the server. And users are allowed to reset their own token whenever they want, but you have to have the user admin to reset someone else's token. Because all of the transport protocols use the exact same JSON messaging implementation, this technically does work with Unix domain sockets and the TCP sockets, but I wouldn't recommend it because they'll all be transmitted in the clear without TLS support. So I would probably only use this with the secure WebSockets support. But you can see an example here. This bitbake hash client command is me resetting my token. So you see I put in the WebSocket address, the WSS address of the server, That's my username. My password's in that secret token variable, and I run the refresh token command, and it gives me back that's my new password that I would have to use next time I wanted to authenticate with the server. Another improvement that we made is that BitBake Hash Server will now accept all of its command line arguments in environment variables, which is sort of a very standardized way that like if you've ever written a Kubernetes service or something like that, this is very common for how to configure a service. Just makes it a little easier when you're trying to implement it on those things. If you do bitbake hashserve-help, it'll tell you exactly what the environment variable is for each corresponding argument. We also have published some container images for all of these things. So these are actually OCI compliant container images that were actually built using Open Embedded, using Metavert, which I've never done before. It was really awesome. If you've never tried building container images with Metavert, I highly recommend it. It's really cool. Yeah, so yeah, it's pretty awesome. So it actually has a recipe that pulls in bitbake and then puts the hash server into a container, using bitbake. Yeah, so it's bitbake building bitbake. It's interesting. And you can actually just pull these down now. If you run these commands, you'll get the hash server and the hash client. Right now, the one that you would want for all the WebSocket stuff is just the latest tag. So just be aware of that. And then these are all in my personal namespace. I would like to find a more permanent home for these that is not my personal namespace. But if you want to play around with it for now, you can do that. Something else that we've done is we added a web management front end. So this is like basically a web UI to manage the server, the hash equivalence server. And kind of the idea behind this is that this uses external authentication to authenticate the users that are accessing the website. And that allows users to self-register and self-service their hash server accounts without having to know what they are. So kind of the idea is you would log into this website using your LDAP account or your OAuth 2 account or whatever you have, and it will let you reset your hash equivalent server token or whatever you are allowed to do with the server without having to actually know what your token is. If you use like bitbake hash client, it won't let you reset your token unless you know what your token is. But this would, because it uses external authentication, it would let you do that. So it just lets people manage their own accounts much more easily. And it'll also let you do some server administration things based on what your permissions are on the hash equivalent server. And this is also there's also a container image for this. It's that bitbake hash server web UI container image that you can run. New subcommands are added to the bitbake hash client. Basically, all of the new support we added, you can access and manage using bitbake hash client. So it's a lot more useful than it used to be. It used to basically just only run the stress command and show the server stats. That's about all it was useful for. Now it's a very comprehensive tool that you can do all the management that you need to do with the server. It also has a nice option to allow you to specify your username and token in your .NET RC. So you don't have to like type it out on the command line all the time. All right, so I do have a quick demo of the web UI. So this is basically a stack that I'm running using Docker Compose. It's going to have a PostgreSQL database running in the stack, and then there's going to be a single instance of the bitbake hash server running with WebSockets on port 9000. And then the web UI talking to that running on port 8000. This isn't doing any load balancing. There's no front-end TLS termination. There's no reverse proxy going on here. This is very simple. It doesn't have the front-end authentication set up to like use an external authentication. There's actually an environment variable you can set for the web UI called this HSUI test user that just says, hey, this is the user. Obviously don't use this in production, but it lets you like test that the web UI works without having an actual authentication mechanism. And if you download the slides, that's the link to the Docker Compose that I'm using if you want to try it yourself. So the first thing you'll notice here is that when I first come to this page, it says it's a new user and I'm not currently registered. So this website allows for self-registration. So users can just go here and click register this user, and then it will create an account, a hash server account for them and give them their token. And then by default, I just set it up to give everyone @read by default. So whenever someone creates an account, the only permission they get is @read, is the read permission. And then they can just do a couple of things, which is they can reset their login token here. And then they can also like delete their account if they want to do that. And it'll say you'll lose your permissions if you do that. Other than that, there's not really a whole lot they can do. So what I'm going to do here is run a command to give my user all admin permissions. The command I'm running is in the slides. If you want to download it, I'm not going to show it on screen because it just wouldn't make sense. Okay, so now I'm going to refresh this page, and now you'll see I have a whole bunch more permissions that I've got here. And so now I can go into this like user administration tab, and I can, create new users. I can assign them default permissions or what their permissions are. I can go here and change their permissions just by clicking on these things. I can reset their login tokens for them. I can delete their account, things like that. I can remove all the permissions that I have. It won't let you delete your own account or your user admin permissions, so that you can't work yourself into a corner where you can't get out of it. But so now if I go back to the home page, you'll see it just says I have user admin, and that's all I can do. Give myself all my permissions again. There's also the database administration. So this will actually show you how many rows are in your databases. So you can see I've got 1,000 out hashes and 0 uni hashes in this particular database. You can clean old database entries. So this will delete entries that are in the out hashes database that are not referenced by any uni hash. So you can say like delete anything that's over a week old. It won't actually, yeah, so I removed all 1,000 entries I had in there. And then you can also remove specific entries by their column. So if you put something in here, it'll remove anything that matches that in the database. So it lets you do some simple database management and removing entries. And then the final page here is just the usage statistics, which just kind of shows you like how fast the server is responding to requests. So that's really all for the web UI. Sorry, I'm going through this so quick, like I got a lot to cover. That's the command I ran. Okay, so the idea of this then is that you can scale this up and run it on basically a Kubernetes cluster. I don't have an example of this, but I have done it. It does work. So basically the idea here is you've got your users, which are over here on the left, and they can access the hash equivalence server proper using this secure WebSocket through your host, and then maybe a hash sub path. And then they can also access like the web UI using this HTTPS/user or whatever, And then that goes into your Nginx, your front end, your reverse proxy load balancer and TLS termination stuff, all that stuff that you kind of use with Kubernetes. You can do your OAuth 2 authentication to authenticate your users, or tie into LDAP or whatever it is that you want to do. And then you can run multiple instances of the BitBake hash server. The hash server is basically completely stateless, so you can just spin up as many copies of this as you want and load balance between them, or have multiple copies for redundancy or whatever it is. You do the same thing with the web UI, and the web UI will internally inside of your cluster talk to the hash server. And then all of this goes out to your big SQL database that you have somewhere else. Or you could also run the SQL database in the cluster too, if you wanted to. So one of the things that we're also working on to make this even more useful is that there are patches in progress to parallelize the queries that are made to the hash server from BitBake. So those initial queries that are made when the run queue is checking every task hash that it's calculated. Currently, that just happens one at a time with the server, which is fine with the current server because the SQLite database, again, is blocking, so you can't go faster than one query at a time anyway. With the new server, the WebSockets and the SQL Alchemy introduces some latency to the process. It's got higher throughput, but it's also higher latency. So the idea is to sort of offset that. BitBake can actually make more than one query at a time. So we have patches in progress that allow it to make it'll be configurable, but you can say oh, query 10 hashes at a time or in groups of 10 or whatever it is. And then that will offset some of that additional latency that's introduced through SQL Alchemy in the WebSockets. And then that'll get load balanced out to your different hash server, different instances of the hash server on the back end, or it could all go to the same one too. If you're using SQL Alchemy, again, there's no blocking, so it should handle multiple at a time. All right, so a couple of the next steps, things that I might like to see in the future. It'd be really cool if there's a Helm chart, so people could just say like, hey, I want to run one of these on Kubernetes, and it just does everything for you. I think that's definitely possible, but I've never written a Helm chart before. I've used them a lot, but I've never written them, so we'll have to look into that. I think the exact same treatment could be done pretty easily to the PR server. Definitely the WebSocket support. The Hash Equivalence server and the PR server actually share a communications library called Async RPC that lives in Bitbake, and that supports WebSockets. So the PR server supporting WebSockets is probably just as simple as telling the PR server front end how to connect via WebSockets instead of whatever it's using now. The SQL Alchemy part might be a little more difficult on the back end of the PR server. But if anyone is interested in that, like I can definitely give you pointers and guide you through that. I don't know much about the PR server, so I don't know. We've talked about adding Python 3 WebSockets to OE core and the build tools tarball so that client WebSockets can be supported on older distros, which I think would be really useful. Or if you're just using the build tools tarball in general, you probably would want the Python WebSockets so you can at least use the client to connect to things. Python 3 WebSockets is nice in that it has very minimal dependencies itself. It basically also just relies on OE core, so it's not a huge Python ball of mess to bring in. I've also got patches in progress to do garbage collection on the server. So this would be adding support for deleting hashes in the server where there is no state file that corresponds to them. So that would allow you to get rid of hashes that aren't useful anymore, particularly since right now the database basically grows unbounded. There is no way to delete them unless you do it manually. So that's something that we've been needing for a while. And then we've also got hash patches in progress to do hash existence checking before hitting the state mirrors. There's been kind of this thing since the Yocto estate is now distributed via CDN. That's great, but state inherently generates a lot of requests for files that simply don't exist, and CDNs really don't like that. You know, those negative hits can be expensive. So one of the ideas that's been proposed is to ask the hash equivalent server if a given hash exists before we go try to pull the state object for it to try to minimize the number of those negative hits that we're making to the state mirrors. Special thanks to Richard for helping me out with some of this stuff and talking me through things. Tim, who suggested that I look at Bootstrap for the JavaScript stuff, the website was much, much, much uglier before he suggested that, so thank you very much. And then Bruce Asheville is the maintainer of Metavert, and again, Metavert is pretty amazing, so I highly recommend it. And he also put up with some patches I posted there. So this is a link to a video I've done on hash equivalence and reproducible builds if you want more information on that.